Right, ladies and gents, welcome to this week's Geotalk. Thanks to John Hancox and CCIC for sponsoring the drinks and the chips. And today we welcome Abigail Barker from Uppsala University in Sweden, who's been visiting us or is visiting us for about a month and a half. And it's been fantastic to have you here, Abby. So thank you for coming and thank you for agreeing to give this Geotalk. Abby hails from the UK, where she did an MSc at the University of Durham and then a PhD at the University of Copenhagen. And she's now, as I said, at Uppsala University. And as you'll hear from her talk today, is very much interested in ocean island basalts, as well as arc volcanism. So some of the most important volcanism on the planet. And so over to you, Abby. Thank you very much.
Thank you. It's great to be here. I'm really enjoying my visit, and I'll soon be planning the next one. As Grant said, I'm now at Uppsala, but some of this work goes back to my PhD days at DLC and the University of Copenhagen. So their logos are there to acknowledge my co-authors. And in the middle, there's a lot of other logos, also people that have contributed to this research. And you notice UCT's logo there, and that's because Chris Harris has been involved. Even closer.
Even closer. That's it.
Is that better? Yes, okay. I can hear that it's right. It doesn't want to go onwards. There we go. So Cape Verde is off of Western Africa. Its closest land point is Dakar. It's about 500 kilometers. And so then we have a horseshoe shape of islands opening out towards the west. And over on the left-hand side of the map, I've labeled the Mid-Atlantic Ridge. So you can see it's a long way from there, but it's also a fair distance from the African continent. The last eruption was from Fogo in 2014. Yeah, it displaced quite a few people, but that's our most recent time point. So we have the Mid-Atlantic Ridge, and below that is the upper mantle. So that has a composition of depleted morb mantle. So it's peridotite, and the geochemistry, both the isotopes and the trace elements, are depleted. And it's crystalline and stable. It's unlikely to melt, particularly in this intraplate setting in the middle of the ocean crust. Then we have the mantle plume, which is essentially a thermal anomaly rising from the lower mantle that may be primitive. And in Cape Verde, it carries with it high mu and EM1. So ocean crusts and sediments that have been eclogized. And it therefore carries a signature of enriched isotopes and trace elements. And the mantle plume carries fertile components that are relatively easy to melt, and creates a hotspot. It may or may not have volatiles, but at Cape Verde, we have quite a bit of CO2. It may even be considered to be a CO2 spot. So if we look at the Cape Verde Islands in more detail, over on the right-hand side, where we have Boa Vista and Sal, these are the older eastern islands. And then we have a southern island chain and a northern island chain. And we can see on this plot, which is the time in millions of years, that it started about 20 million years and particularly in this area on the east. And then in the southern island chain, as you move southwest, the islands get younger, and the northern island chain, as you move northwest, the islands also get younger. And all these black bars are argon dates, whereas the gray are potassium argon, so less reliable. So we have an age progression in this direction, but because the plate is moving quite slowly, we don't see a strong age progression like at Hawaii. We're also close to the pole of rotation for Africa in the Cape Verdes, so that contributes to the slow speed. So if we think about the ocean crust, when it started drifting, it was 180 million years ago, just off of the continental shelf of Africa, and new crust is being produced today at the mid-Atlantic ridge. So the crust that the Cape Verde Islands sit on is 130 to 135 million years old. So there's 35 to 40, about 40 million years between the oldest crust and the crust that Cape Verde is upon. The ocean crust also has Cretaceous sediments on it. The pile is about 2 kilometers thick. How do we know it's a mantle plume involved here? Well, there's anomalous heat flow, also a geoid anomaly, and topographic or bathymetric variations. So it's essentially a 2 kilometer high plateau above the seafloor. And also there was some seismic tomography work done. And you can see on the picture on the left, they've named the Cape Verde plume, the Canaries, and the Azores. And you can see below the surface, there's 3 anomalies. And as you go down into the lower mantle, some kind of anomaly persists, which given the resolution they have is quite significant. We also have some helium data. So a mid-ocean ridge basalt or the ocean crust would have a 3-4 helium ratio of about 8 R over RA. And in the northern islands at Cape Verde, we have values up to 15. And in the southern islands, we have values up to 12. So this is suggesting that we have some primitive mantle brought in with the mantle plume. A while ago, well, in the late 80s, people discovered that there was heterogeneity in the Cape Verde Islands. So the northern islands in blue here, they have high 206, 204 lead from the radiogenic ingrowth. And that correlates with epsilon neodymium, giving a negative correlation between high mu and depleted mantle. Whereas the southern islands, they have lower 206, 204 lead values and extend away from this line, the Northern Hemisphere reference line, towards an EM1 component. And so that EM1 component has low epsilon neodymium. So this gives us heterogeneity on the scale of 100 to 200 kilometers. The high mu we think of as recycled ocean crust. Depleted mantle, or DM, is the upper mantle, and EM1 is often considered to be subductive sediments, but I'll expand more on that later. So in the northern island chain, we have high mu and depleted mort mantle. In the southern chain, we have high mu and EM1 as the dominant components. And if we look at delta 18O in mineral separates, we can see here that the high mu end member has relatively low delta 18O, about 4.9, whereas the EM1 M member has about 5.4. And we can then see some correlations with trace elements that also confirm that this low delta 18O value is high mu. And if we look at this figure, delta 18O of clinopyroxene with barium niobium ratio, we can see that the EM1 with a high delta 18O and has high niobium, barium niobium, so suggesting some sediment input as EM1 or potentially a role for carbonatites. So what I want to talk about today is how we can determine the influence of the mantle plume on the mantle heterogeneity, the mantle lithologies, and their interactions at Cape Verde. So I'll talk about the spatial and temporal variations, go on to look at the source lithologies, and then the intrasample heterogeneity. And yeah, so it's the story of what happens to the upper mantle as the mantle plume invades. So when it comes to mantle sources, we have peridotite in the upper mantle, and the mantle plume is going to introduce eclogite as the recycled ocean crust. And eclogite can melt very deep, so at about 150 kilometers already, and then it interacts with the peridotite, forming a pyroxenite. And then as that rises, the pyroxenite then melts, and at the most shallow depths, the peridotite will melt. So we have this process of fertilization of the upper mantle peridotite by an eclogite melt. And this leads to high nickel and high iron oxide pyroxenites, or often called hybrid pyroxenites. And if we look at nickel or manganese contents just with phosphorite content of an olivine, we're going to see fractional crystallization trends. So what we do is we make ratios. So manganese divided by iron oxide and nickel multiplied by iron oxide divided by magnesium oxide. So this corrects for the fractional crystallization. A partial melt of a solid eclogite. Yes, and I'll show you more about that later. But on this figure, I've got magnesium divided by iron oxide on the y-axis and nickel star on the x-axis. And the gray diamonds are from Sobolev's data sets, so they're global oceanic basalts, or olivines from global oceanic basalts. So I often refer to this as the global array. And so a peridotite would plot at relatively no nickel and high manganese over iron, whereas our hybrid pyroxenite would plot at high nickel star and low manganese. So the mantle plume rises through the upper mantle to create a hotspot. But there's another feature of Cape Verde, which is very interesting, and that's the presence of carbonatites. So we see them as milky white lavas that are very thin in a few places, but they're most common in the on the island of Brava, where we have carbonatite dikes and an intrusive complex with things like servites. Thank you. And so when you have carbonatites around, they melt even earlier, and then they carbonate all of the things that are around, so the peridotite and the eclogite. And then carbonated eclogite will be more fertile, so it will melt deeper, and then carbonated peridotite will melt, and you also get silicate melts from carbonated eclogite. And our hybrid pyroxenite, if it's dry or anhydrous, then it still melts before the dry peridotite. And so on the right-hand side graph, you can see temperature increasing to the right and depth increasing downwards. And our mantle plume is likely coming up this line. So it's got a way to go before it can cross the pyroxenite and peridotite liquidus, solidus. But in contrast, the carbonated peridotite and eclogite melt at much lower temperatures. So let's have a look at the archipelago scale heterogeneity from a spatial and temporal perspective. So I'll talk first about the Cadamosto seamount off of the southwest of the Cape Verde Islands, and then compare Santiago with Santo Antão, because we have the best time records from there. So we would expect the Cadamosto seamount to plot with the southern islands, because it's right next to Fogo and Brava. But what we find is that it actually plots like the northern islands, which is quite good fun because it suggests that we have a very spatially constrained EM1 component. So not the northern islands and Cadamosto have a high mu and depleted morph mantle signature, whereas only a few of the southern islands, Mayo, Santiago, and Fogo, have high mu with the EM1 component. We use Santo Antão from the Northern Islands as a proxy for there because we have the best time records. And for the Southern Islands, we use Santiago again because we have good time records. And the volcanics there are split into several age groups. So we have the old volcanics at 7.5 to 2 million years from Santo Antão. And at Santiago, they're 4 to 5 million years. Then we have the intermediate volcanics, 2 to 0.3 million years in the north, and in the south, 2 to 3 million years. And then we have a set of young volcanics, often volcanic cones, and they are 1 million year or less in age. So here's a picture of some of the Santiago, beautiful pillow lavas where you can really see what's going on much better than other things. So, and here I have 206 lead, 208 lead, and this line that divides the northern islands from the southern islands. And so these are the old volcanics from both places. So you can see they have high 208 over 204 lead for both the north and the southern islands. When we add the intermediate ones, we find that this high 206, 204 lead signature has decreased its 208, 204, both in the northern islands and the southern islands. And then as we come into the young volcanics, we find that in both places it shifts back in between the old and the intermediate volcanics. And we looked at the 207, 204 lead in relation to this Northern Hemisphere reference line, and there it's constant. We don't see these variations. So that suggests we have a single age of the recycled oceanic crust. So this divide between the composition of the southern islands and the northern islands has been around for at least 4.6 million years. And so if we think about that in terms of what's happening in the mantle, what the heterogeneities might look like, the high mu has been present in the northern islands for 7.5 million years, as much as we know. So if we take a mantle upwelling rate of 10 millimeters per year, that would suggest that the heterogeneity has a vertical extent of about 75 kilometers. In the southern islands, we've had EM1 and high mu together for at least 4.6 million years. Again, with a similar upwelling rate, we would suggest that that heterogeneity is about 50 kilometers. And that we've had both high mu and EM1 sampled continuously during that time. So here on the right is my little cartoon to show that. But that kind of seems crazy, right? How do you have those kind of anomalies? People that have studied these things in terms of their dynamics and numerical modeling and things say that heterogeneities that are large enough to survive mantle convection are large enough to segregate melts. And also that you only need something on the order of 6 kilometers to survive convective overturn in the mantle on the order of 960 million years. So our Cape Verde heterogeneities are pretty much 10 times that. So they should definitely be able to survive mantle convection for a billion years. And it's unlikely they're in this exactly the same state as when they were subducted. And Fantani and Samuel showed that in a numerical model, you would share heterogeneities. So they would actually become longer, of course. And that also allows you to have different heterogeneities spatially. So that would help to explain why we've got the EM1 component in such a small area over a long time. What are these? What's the plume made of? Thank you, De Beers. I saw this nice photo yesterday and thought it would illustrate my presentation well. And here's a beautiful section of pillow basalts and hyaloclastites as well. So let's look at the source lithologies. So we know we have high mu, depleted morb mantle, and EM1. We also have carbonatites in Cape Verde, so they may well be playing a role. So our depleted morb mantle is peridotitic. The recycled ocean crust, the high mu component, is likely eclogite, and the EM1 subducted sediments should also be eclogite. And we know that this eclogite, when it melts, it reacts with peridotite to form pyroxenite. But is this all a well-mixed situation, or do we get some sealing of pathways so that we can preserve melts derived from things like eclogites? So we'll look at some whole rock geochemistry versus some experimental results. So here the samples are from Santiago, and we can see different experimental melts marked on all of these diagrams. And this one with titanium on the y-axis is perhaps the clearest, where we have peridotite and carbonated peridotite, and much lower titanium. Pyroxenite has a bit higher titanium, but to produce these samples, we seem to need carbonated eclogite. We also see in silica that the low silica samples only really plot in the carbonated eclogite melt field. We also have melt inclusions, and we have some ultramafic melt inclusions here in the green. And the orange is the whole rocks, and these samples are from Fogo. And the ultramafic ones are mostly hosted in olivine. As we can see here, they span a whole range from peridotite to carbonated eclogite melts. So the peridotites have high magnesium and low titanium, and the carbonated eclogites have much higher titanium. We also find some very evolved melt inclusions. So these are felsic, they're less than 2.5 weight% magnesium. And so they're phonolites. They're very high silica, aluminium, potassium, and sodium, and they're mostly hosted by clinopyroxenes. So this is interesting that we mostly have ultramafic melt inclusions in the olivines and mostly highly felsic ones in the clinopyroxenes. But there are a few exceptions. So carbonatites, they contribute as melts and mix in with the magmas. And so we can see down here in barium versus barium over thorium ratio. So we've got the Fogo samples in the red, and high mu are these purple hexagons. The green triangles are EM1 from Tristan, and the gray diamonds are EM1 from Pitcairn. So we can see the Fogo samples in red. They're extending to higher barium-thorium ratios than the other components or the other locations, and pretty high barium. So the only source I can find to fill this blank area is carbonatites. We also see that here when we plot with titanium europium, that we need a high barium source, and sometimes it's heading towards low titanium uranium. So it looks like we need a distinct carbonatite phase to mix into these silicate melts at some point. So then with the trace elements for the whole rocks, I went on to model them to find out what's required to produce these whole rock samples from Fogo, and also to look at the end members, high mu and EM1. So in the black lines, we have peridotite melts and carbonated peridotite melts in these dashed lines. In the gray, we have eclogite melts and carbonated eclogites. And in the red, we have pyroxenite melts. So we can see the EM1 component is between peridotite and carbonated peridotite, and comes to some eclogites, carbonated eclogites, and the high mu component is strongly eclogitic, so melts derived from an eclogite. And this is both for the mafic and felsic melts. And there's also some places where we can't reproduce the melts just from those lithologies, and so it's likely that carbonatite melts are mixing in here as well, and having a role in carbonating the peridotite and eclogite. So then I turned to olivine to see if I could trace the mantle sources. So we used a high precision protocol for analyzing olivine by electron microprobe. So we used a super high current, and we analyzed the nickel and manganese for 3 times 60 seconds. So super long counting times here. On the top, I have Santiago, and on the bottom, Santo Antão. And we can see the olivine contents plotted with manganese and nickel. So we have negative relationships with manganese in both the North and the South Islands, and positive relationships with the nickel. And then, of course, when we calculate the parameters of nickel star and manganese star, we see that these totally flatten out. So it's not, those are not controlled by the fractional crystallization. So then I plotted these samples over this global array for olivines. And we can see that some of them are close to the global array, but they really dip down here to very low nickel star and manganese star. And the only component I've been able to find is melts from eclogites, which have these very low values. And this is occurring in both the North and the South Islands. So then I calculated the proportion of eclogite in the samples and find for depleted morph mantle in the middle here that we have 35% peridotite, 25% pyroxenite, and 40% eclogite. For our EM1 component, we have 25% eclogite, 35% pyroxenite, and 40% peridotite. So the involvement of an eclogite component there suggests it is a deep source. And our high mu component has, of course, the widest range, but somewhere between 45 and 65% pyroxenite to peridotite, and up to 65% eclogite. And it's interesting that these younger samples have higher proportions of eclogite. And so the eclogite melt showing up here is kind of similar to that process of carbonation. So of using a carbonatite melt to metasomatize the peridotite and the eclogite. If we go on to look at olivine from Fogo, we have to switch this around. So we have nickel star on the y-axis and magnesium star on the x-axis. And again, the gray diamonds are the global array. So we see in these light green olivines from Fogo that they plot at the peridotite end of the array. But then we have these dark green samples, which are extending to much higher manganese star. And the only thing we could find like it was carbonated peridotite. So olivines in lucites from a carbonatite province. So this is suggesting that the olivines are peridotitic in nature, derived from peridotites, and that the peridotites have been carbonated as well. We noticed that the clinoperoxenes that go with these hosted more than 50% of the nickel. So we wanted to find out, well, what would an olivine that grew in equilibrium with these high nickel clinoperoxenes actually look like? And it turns out when we calculate the equilibrium olivine that it has high nickel star, and it is plotting as a pyroxenite. It's not letting me go on. Yes. Okay, so then if we look at compositions of clinoperoxene from Fogo, we can see that the purple triangles are our samples, and they're very similar to the clinoperoxenes in the pink triangles that are from clinoperoxenites from Brava, the island next door. And on the top right, we can also see scandium over manganese divided by zirconium versus zirconium divided by scandium. And here we see that the green triangles that are the clinopyroxenes from Fogo span between carbonated peridotite and carbonatites. And they plot very similar to the open purple triangles, which are again the clinopyroxenites from the adjacent island of Brava. And we also see there in the lilac triangles some pyroxenite derived clinopyroxenes from the Canary Islands. It doesn't seem to want me to go on. Yeah, I think it's on. Okay, so the trace element ratios are similar to clinopyroxenes from the Brava clinopyroxenites. And so this is an indication of a pyroxenite source lithology. So if we look then at the scandium as a tracer of clinopyroxene, when we have high scandium, we tend to have low zirconium, gallium, zirconium, scandium, and hafnium, gallium ratios. And then if we plot those ratios against delta nickel values, we find that that corresponds to the low light delta nickel. Yes, so that again is suggesting a pyroxene-rich source from the scandium, and that has a light delta nickel value. It's we see a glimpse of the EM1 from the very felsic melt inclusions. So they're phonolytic. And on the diagram on the right, which is a Shand index diagram, we expect fractional crystallization to go from the northwest quadrant or northwest corner in towards the middle. And the green samples, green circles are the phonolytic melt inclusions, and they seem to be making a trend along the dark red arrow. And so if we look towards the northeast quadrant, that's up towards some paraluminous glasses that have been found in Mantle xenoliths. So I think that this is a mixing trend and that we have a contribution of this very paraluminous melt, which would likely be derived from pelagic sediment. We also see correlations between delta nickel and things like barium niobium, where the high end at light nickel is also an indicator of a sediment source. So yeah, where does the EM1 component come from? If we have only ocean crust underneath the Cape Verde Islands, which is what it seems to be, it could be mid-ocean ridge basalt compositions, and it could have had some carbonatite metasomatism. If there was some delaminated subcontinental lithospheric mantle around from the breakup of Africa, then it would have similar barium lanthanum ratios and epsilon neodymium ratios to the recycled ocean crust. It would have had to have 180 million years residence in the upper mantle, but we don't see this in the mid-ocean ridge basalt compositions. The carbonatite component is also from a mantle or a high mu source, not from a metasomatized subcontinental lithospheric mantle. And also, if we have this component around in the mantle, it would have dispersed, and it would be unlikely to give us that geographical restriction of EM1 to the 3 islands in the south. Yep, so there's 40 million years between rifting and the production of the Cape Verde oceanic crust. And then until 20 million years before the Cape Verde mantle plume created the hotspot. And we get continuous supply of EM1 over 5 years, and it has a uniform composition. We also have evidence that the EM1 component has a deep source from its eclogite composition. So just briefly to sum that up, we have peridotite to carbonated peridotite, we have pyroxenite, we have carbonatite, and we also have a sediment melt involved in Cape Verde. So let's have a quick look at the mineral scale heterogeneity. So we find a lot of disequilibrium between individual samples. And so here my examples are going to be mostly Fogo, but also a little bit from Santiago. So we have these 2 mineral populations from Fogo. So our olivines, the peridotites, and the olivines that would be in equilibrium with our pyroxenes. So really are finer pyroxenes. And they have a completely different composition. And yet we find them in the same erupted rocks. The lab doesn't like to let me in, but this doesn't like me to change slide either. We also have our melt inclusions where we have 2 completely different compositions. We have the ultramafic ones associated with olivine and the clinoperoxene hosted ones that are likely a sediment melt. So it was around pretty early in the system when clinoperoxene was crystallizing. When we looked at the oxygen isotopes, we find that clinoperoxene is out of equilibrium with olivine. So it should be in this mantle field, but the clinoperoxene has lower delta HCO. The olivine and ground mass are pretty much in equilibrium, but when we plot clinoperoxene with ground mass, we find a wide range of fractionation factors from what we expect for a basanite or nephelinite, all the way to what we expect for a phonolite, which is kind of interesting. So the delta 18O of olivine and pyroxene correlates with completely different trace element ratios. So they seem to be behaving differently. We seem to have a correlation with barium niobium for the clinoperoxene, whereas we have correlations with things like uranium thorium and zirconium yttrium in olivine. So these seem to be completely different systems, but we find them together. Also, a while back, and we didn't realize the significance to start with, we found that in the lead isotopes, when we measured duplicates and also clinoperoxene separates, that we had significant heterogeneity, significant differences. So these bottom diagrams are the difference between one of the ground mass samples and either its duplicate or the clinoperoxene. And the small boxes, that's where the standard errors are. So we can see that there's a lot of crystals and even ground mass that go beyond the analytical errors in the lead isotopes. We are in with the nickel isotopes and the relationships or correlations with some of the trace element ratios. we also find trends, essentially binary mixing trends. And so that's suggesting that, yeah, we've been mixing things. So what seems to have happened is we've had mixing between an olivine, an ultramafic melt inclusion magma batch, and another magma batch containing clinoproxene and the phonolytic melt inclusions. And that also, yeah, so that connects both with the recycled ocean crust, the pyroxenite, and the sediments, whereas the olivines are more of the peridotite end member. What we see is that EM1 is restricted to 3 islands in the south, Fogo, Santiago, and Mayo. We see that high mu changes systematically with time over the whole archipelago, and that the recycled ocean crust components are on the order of 50 kilometers. We have various evidence for different mantle lithologies that are potentially carbonated or formed by reaction, including carbonatites and sediment melts. And we find the minerals, the melt inclusions, and the whole rocks are all recording different parts of the system. So we've had a magma carrying the olivine and the ultramafic melt inclusions mixed with a magma that's carrying the clinoproxene and felsic melt inclusions. And together they make the whole rock. So we've had carbonation of the peridotite upper mantle, and it's mostly the olivines that have crystallized from that. On the other side, we've had eclogite melts creating pyroxenite, sediment melts also coming from this recycled ocean crust, and they seem to be mixing and at equilibrium in another magma chamber. And then before it gets erupted, then the eruptions seem to take samples from both of these systems. And a little bit about what I'm doing at the moment. So I'm working on the Nola seamount, so that's off of the island of Santiago. It's a twin-peaked seamount, and I collected the samples with the DFG-funded meteor expedition, and some of them were collected with this nice little ROV. And so here I'm preparing some samples for iron isotopes. I have both whole rock samples, and also I've used this micromill to drill some zones in clinoproxene. So what I want to do is determine the interplay between the mantle components and their lithologies. And the seamount at Nola should have the high mu and the depleted malt mantle, but should not have the EM1 component. So this will be quite interesting to study that further. And I've put some examples then on the left of delta 56 iron for morb, so our depleted morb mantle, and EM1 from Pitcairn. So that goes slightly heavier. And then these two diagrams in the middle at the bottom are from clinoproxene. And we see clinoproxene derived from peridotites has light delta 56 iron, whereas clinoproxene from pyroxenites has heavier delta 56 iron. So this, I'm sure, will be an interesting conundrum to have a look at. Thank you.
Okay, thank you so much, Abby. Do we have any questions from different audiences? Lou?
Thank you. The occurrence of carbonatite here is really weird because 99% of the Earth's carbonatite occurs in the continents, and it is thought to have been derived by partial melting in the subcontinental mantle lithosphere. So I guess there's two questions. Why is Cape Verde so unusual such that it would allow the production of carbonatite in an oceanic setting, unless, of course, there's a piece of SCLM in there, and that could answer it. But then you're going to want to know why you don't find it in any other ocean islands. I think there's one shitty little report of a carbonatite something in Hawaii, but I don't know about any carbonatite elsewhere. So let's hear that.
Okay, thank you for that question. So the lithosphere is relatively thick in Cape Verde, much thicker than we see at most of the other ocean islands. And so that means that we have a smaller window, a smaller melting column. So we see the things that happen first, whereas at Hawaii, we have a smaller melting column. So we see the things that happen deepest and first at Cape Verde, whereas in Hawaii, we've got a much longer melting column because of the much thinner ocean crust and lithosphere. So that means that anything that happened deep gets diluted as you go up the melting column. The carbonatites in Cape Verde have also been shown to have mantle signatures from their lead isotopes. So their lead isotopes are very similar to high mu, even more extreme, but also their noble gases, noble gas isotopes. They are mantle derived.
All carbonatite comes from mantle.
But you were asking about the subcontinental lithospheric mantle.
What do you mean by mantle when you say the word mantle?
Asthenospheric mantle.
Okay, I don't think that any carbonatite comes from a asthenospheric mantle. But it's a point of contention, I know, about carbonatite. Okay, another question would be your boundary between north and south. You have a geochemical discontinuity there. And I wonder if you have thought that this might be similar to the kind of thing they're finding in Hawaii, mainly the work of Dominique Weiss, who thinks that, and you can explain this to me if you can, but she thinks that that the mantle plume in Hawaii, which comes from the core mantle boundary, is actually sampling two different mantle sources. And that dichotomy is preserved all the way up through 3,000 kilometers, and it is expressed as the Mauna Kea trend and the Mauna Loa trend. I don't know. Is this something similar?
Yep. This is essentially the same thing.
What?
This is essentially the same thing. So we have the AM1 being constrained to one side, to a small area. But over the time scale that we have sampled, it seems to be constant. And so, yes, I would suggest, just like Dominique Weiss.
It seems a little weird to me that why these two solid rising components would not blend with each other in that 3,000 kilometers, but I guess they don't.
I guess I had a follow-up to Lou's question, and that's about earlier you suggested that you were suggesting that there was almost like a preservation of fragments of those different components, as opposed to them coming all the way from the core mantle boundary source. They were fragments that might be transported by convection and melt at some point in the column. I'm wondering if you think your components are coming all the way from the source, the origin of the plume, or if they could be fragments of EM1 and high mu that are discrete fragments that are being transported convectively. and melting.
Yeah, so I think they're large fragments. So yeah, on the order of 50 kilometers. And we don't seem to see an episodicness in them over time. It seems, yeah, quite constant. So I think it would be hard to do like the melange model from a subduction zone to create the this kind of heterogeneity that is picked up by a mantle plume. But I do think that the melange model would be great for heterogeneity in the upper mantle. But then that is very similar to if you have some subcontinental lithospheric mantle delaminating. And we don't see that in the Morb source in this area.
Okay. Fascinating.
This piece of SCLM that you keep mentioning, tell me about where you think that is or was.
Well, so
is it still there?
The idea is that it's formed by edge-driven convection when the African and South American plates split apart.
It's fine.
But yeah, I've done some modeling of the mantle flow, and it would have moved away from Cape Verde in the time frame that we have, and also it seems extremely difficult to constrain the M1 component to those 3 islands if you've got blocks of subcontinental lithospheric mantle drifting around. So that's my thinking on it.
So I'm still not clear. Where is this piece of SCLM? Is it there now? At what depth?
I don't think it's there. I don't think that is the main contributor. Because yeah, you don't see it locked into the ocean crust. And why would it just come up under those 3 islands? Okay. So I'm more a believer that it's been recycled through the mantle.
Right. Any other questions from the audience here or online? If not, then Abby, thank you so much. It's going to be exciting to see the iron isotope story emerging.
Yes.
And hopefully the next talk can be about iron isotopes measured here at Wits. So thank you, Abby.
Thank you.